Owls solved one of the hardest problems in aerospace engineering 60 million years before humans even existed, and we're still trying to figure out how they did it. These remarkable birds can fly so quietly that a barn owl swooping toward you won't produce enough sound for your ears to detect until it's about 3 feet away. 3 feet, that's roughly the distance between you and your phone right now. By the time you hear the whisper of those wings, it's already over. For decades, engineers have been studying these birds, borrowing their secrets for bullet trains, wind turbines, and military drones. Siemens Gamesa has even deployed dino-tail serrated wind turbine blades inspired by owl feathers, proving this isn't just lab research anymore. But here's the wild part though, Tam. We've made incredible progress, but according to the actual scientists working on this, we might not even fully understand the most important reason owls are so quiet. So let's break this down, from 60 million years of evolution to the cutting edge of modern engineering, and see what happens when nature's oldest stealth technology meets human innovation.
To appreciate what owls are doing, you first need to understand why flying is loud in the first place. Every bird that moves through the air creates turbulence. Air flows over the wing, separates at the trailing edge, and generates pressure waves. Those pressure waves hit your eardrums as sound. For most birds, this isn't a problem. A pigeon doesn't care if you hear it coming. An eagle circling at 1,000 feet isn't worried about noise complaints. But owls hunt differently. Many species are nocturnal predators that rely on pinpointing the faintest rustle of a mouse moving through dry grass. They need to hear that sound, and they can't hear it if their own wings are drowning it out. So sometime in the deep evolutionary past, owls began developing something remarkable: wings that cheat the laws of aerodynamics. The earliest undisputed owl fossils date back roughly 60 million years to the Paleocene epoch, though some estimates push the origin of the owl lineage back as far as 68 million years ago, right around the time the dinosaurs were bowing out. Those early owls looked nothing like the ones we know. A fossil species called Promoptynx poliatoros, which lived about 55 million years ago, was more hawk-like than owl-like. Early Eocene owls had eyes that weren't as enlarged or forward-facing as modern species, and they probably couldn't even rotate their heads with the dramatic range we associate with owls today. Some of them were likely diurnal, hunting during the day. So what changed? During the Eocene epoch, roughly 56 to 34 million years ago, owls underwent a massive diversification. As they spread across the planet and adapted to different environments, many lineages shifted toward nocturnal hunting. With that shift came new evolutionary pressures. If you're hunting in complete darkness, you need 2 things: incredible hearing and the ability to fly without masking what you're listening for. The owls that could do both survived. The ones that couldn't, didn't. Natural selection is brutally simple like that. By the Oligocene and Miocene epochs, 34 to 5 million years ago, ancestors of familiar modern genera like Strix, the wood owls, and Bubo, the eagle owls, start showing up in the fossil record. These are birds that had millions of years to refine their engineering. By the time modern species emerged, they had perfected 3 specific adaptations that, to this day, human engineers are still trying to replicate. In 1934, a British pilot and bird enthusiast named Robert Rule Graham published a paper in the Journal of the Royal Aeronautical Society that would quietly become one of the most important documents in biomimicry, a field that wouldn't even be formally named until Janine Benyus coined the term in 1997. The paper was called The Silent Flight of Owls, and in it, Graham identified 3 structures on owl feathers that seemed to explain their stealth: the comb, the velvet, and the fringe. 90 years later, those 3 features are still the foundation of everything we know about owl silence. The comb is a serrated, tooth-like structure along the leading edge of the owl's primary flight feathers. If you look at an eagle feather under magnification, the leading edge is smooth. An owl feather looks like a tiny saw blade. What this does is break incoming air into smaller microturbulences before it flows over the wing. Instead of air hitting the wing and creating one large, noisy vortex, it gets divided into many tiny currents that essentially cancel each other out acoustically. It's the same principle behind why a waterfall roars, but a gentle rain barely whispers. Same amount of water, different turbulence structure. The velvet is a soft, velvety coating on the upper surface of the owl's wing feathers. This porous, downy layer acts like acoustic dampening foam, absorbing sound energy that would otherwise radiate outward. Thomas Geyer, a leading aeroacoustics researcher at Brandenburg University of Technology in Germany, tested this by creating a wing the size of an owl's with a similar poroelastic surface, and found it was 2 to 5 decibels quieter than a standard wing. That might not sound like much, but decibels are logarithmic. A 10 decibel reduction is like turning the sound of a passing truck into the sound of a passing car. Even a few decibels represents a significant reduction in perceived loudness. The fringe consists of ragged, comb-like structures along the trailing edge of the feathers. These fringes soften the sharp boundary where air leaves the wing, reducing the turbulent wake that normally creates most of the noise in flight. Research published in November 2023 in the journal Bioinspiration and Biomimetics detailed how these microfringes work at a level of precision we're only now beginning to fully map.
Quick thing before we keep going. If you're enjoying this, subscribing is completely free and it really helps us out. I appreciate it, thank you. Right, let's get back into it.
Then there's a fourth factor that Graham didn't emphasize, but that modern researchers consider crucial. Owls have enormous wings relative to their body size. This means they can fly incredibly slowly without stalling. A barn owl, for instance, can cruise at just 2 miles per hour. For perspective, the average human walking speed is about 3 miles per hour. These birds are literally flying slower than you walk. Slower flight means less turbulence. Less turbulence means less noise. When you combine all four of these features, the result is staggering. Measurements show that owl wings suppress noise specifically at frequencies above 1,600 Hz, which on a piano is about 2.5 octaves above middle C. This happens to be the frequency range where prey animals like mice and voles have their sharpest hearing. Evolution didn't just make owls quiet, it made them quiet in exactly the right way. Now here's where it gets really interesting. There's an ongoing scientific debate about why owls evolved silent flight in the first place, and the answer might not be what you think. The obvious explanation is stealth. Fly quietly so your prey doesn't hear you coming. That's intuitive. That's what most people assume. But recent research actually slightly favors a different hypothesis called self-masking. The self-masking idea goes like this. Owls don't just need their prey to not hear them. Owls need to hear their prey. If an owl's wings are generating even moderate noise, that noise masks the faint sounds of a mouse rustling 20 feet below. By suppressing their own wing noise, owls essentially turn their bodies into mobile listening stations. They're not just predators, they're biological surveillance platforms. Christopher Clark at the University of California, Riverside has been doing fascinating work on this, and he's pointed out something that supports the self-masking hypothesis beautifully: fishing owls. These are owl species like Blakiston's fish owl, Bubo blakistoni, and Pell's fishing owl, Ketupa pelli, that hunt fish, and they've actually lost their silent flight adaptations. Their feathers lack the comb, the velvet, and the fringe. Why? Because they hunt at the air-water interface, where ambient noise from splashing and flowing water is already so loud that wing noise is irrelevant. They don't need stealth because their prey can't hear them anyway. They don't need to eliminate self-masking because they're hunting visually, not acoustically. It's a perfect natural control experiment. Owls aren't even the only birds that figured this out. Some species of Australian frogmouths, which are carnivorous birds, independently evolved the exact same adaptations. Soft, fluffy wings with combs and ragged fringes. For a long time, scientists assumed frogmouths must be closely related to owls, but genomic analysis proved they're not. This is convergent evolution, two completely separate lineages arriving at the same solution to the same problem. As Clark put it, evolution often takes a quirky path. But one way you can identify the underlying mechanical principles is through convergent evolution. So that's what nature figured out over 60 million years. Now let's talk about what humans have done with this knowledge in the last few decades. The most famous example is Japan's Shinkansen bullet train. In 1989, when these trains were pushing 170 miles per hour, they had a serious problem. Every time a train exited a tunnel, it generated a massive sonic boom that rattled windows and disturbed residents for miles around. The noise was so severe it threatened to derail the entire high-speed rail program in a country with some of the strictest noise regulations on Earth. Enter Eiji Nakatsu, the general manager of technical development at JR West and a passionate birdwatcher. Nakatsu recognized that the pantograph, the arm on top of the train that connects to the overhead electrical wire, was one of the biggest noise sources. He knew exactly where to look for a solution. In his own words, "I learned that the owl family has the most silent flyers of all birds." His team studied owl wing serrations and applied the principle to the pantograph design. It took 4 years of what Nakatsu called strenuous effort by his younger engineers to translate biology into engineering. They inscribed serrations onto the main part of the pantograph, and in 1994, the owl-inspired wing graph replaced the traditional design. When the 500 series Shinkansen entered service in 1997, it ran at 300 kilometers per hour, a world record at the time, while meeting those impossibly strict noise standards. Biology had solved a problem that pure engineering couldn't. Graham had predicted something like this back in 1934, when he wrote in the Journal of the Royal Aeronautical Society, "It would be a mistake to ignore birds as a guide to possible future developments." He was 60 years ahead of his time. Today, the applications are expanding rapidly. Justin Jaworski, who began studying owl wings at Cambridge in 2010 and now collaborates with Ian Clark at NASA Langley Research Center, has created 3D-printed attachments inspired by owl feather structures that can reduce wind turbine noise by roughly 10 decibels. To put that in perspective, Jaworski and Cambridge colleague Nigel Peake noted in their 2020 review paper that a 10 decibel reduction is like turning the sound of a passing truck into the sound of a passing car. For onshore wind turbines, which are currently heavily braked to reduce noise pollution and therefore run less efficiently, this is transformative. You could potentially run turbines at full speed without exceeding noise limits. In May 2024, a study published in Nature Communications took things even further by combining owl feather serrations with the wing geometry of cicadas. This hybrid design achieved up to a 5.5 decibel reduction in overall sound pressure levels and increased propulsive efficiency by over 20% compared to industry benchmarks. Some configurations hit nearly 10% noise reduction with a 48% improvement in propulsive efficiency. Those numbers are remarkable. Then there are drones. Engineers at the University of Surrey are running a project called Learning to Fly, studying how owls and hawks navigate tight spaces and turbulent winds, then using machine learning to teach fixed-wing drones to replicate those abilities. Olaf Markson, one of the researchers, put it simply, "Nature has already solved many of the challenges we face in drone flight. For energy companies inspecting offshore wind farms, for delivery services navigating urban environments, for any application where quiet, agile flight matters, owls are providing the blueprint." Airbus has even built a prototype called Albatross 1, with hinged wingtips inspired by owl feather responses, designed to reduce the effects of turbulence on commercial aircraft. Passive feather-like flaps are being tested on experimental aircraft. The owl is slowly, quietly reshaping aviation. But here's the humbling part. Despite all of this progress, Christopher Clark, the biologist at UC Riverside, has cautioned that engineers may not even have identified the most important source of noise in owl flight. The engineering view, informed by fluid dynamics equations and wind tunnel experiments, and the biological view, based on anatomy, behavior, and genomics, haven't fully converged yet. A truly integrated understanding will probably require both perspectives working together. We've been studying these birds for 90 years since Graham's paper, and we're still catching up to what evolution accomplished through trial and error over millions of generations.
There are 254 recognized species of owl spread across every continent except Antarctica. They range from the 5-inch elf owl to the 2-foot Eurasian eagle owl. Right? Humans painted them on cave walls in France 15 to 20,000 years ago. Their feathers are so valued that possessing one without a federal permit is illegal in the United States under the Migratory Bird Treaty Act. After 60 million years of refinement, after evolving 3 distinct feather structures that suppress noise in exactly the frequency range their prey can hear, after inspiring bullet trains and wind turbines and military drones and commercial aircraft, these birds still fly overhead in the dark. I'm about to tell you something absolutely mind-blowing. We like to think of engineering as a human invention, but the owls were engineers first. They were just quiet about it. Well, that's all for today. I hope you have enjoyed. Don't forget to hit the subscribe and watch other amazing videos in this channel. Thank you, and see you soon.